Good afternoon, and first of all, I thank the organizers for coming up with this beautiful idea and inviting me. I am very pleased to be here with, in a meeting which celebrates the enormous achievement of Chandan and Chris over a very long period of time and spreading the light of the knowledge, condensed matter physics, not only in India but also throughout the world. And I have been fortunate to know Chandan also since very long time, and fortunate to have interacted with him on so many occasions. And not only he's a great researcher, he's enormous knowledge, but he is a very nice human being, and it's a pleasure to know him and interact with him. So I'm going to talk on charge transport in disordered organic systems. And this is based on collaborative work with Dr. Rajmohan, who does experiments and also does simulation, and Dr. Mukesh Joshi, who heads this lab of photovoltaics. So in organic semiconductors, you have basically, because of conjugated bonds, alternating carbon bonds, single and double, sometimes triple also, which gives rise to electron density. And the process by which the charge transport happens is mostly believed to be hopping of the states between various localized states. And these materials have become very important because of the fact that now you can make materials with the property you want. You can tune the mobility, conductivity, and you can do anything you want to do with them. And people have hoped to replace all the electronics with what is called plastic electronics. So a lot of interest these days in these systems. So as I said, you have the charge transport is through hopping, and this was proposed way back in 1993 by Basler. And you still replace this disordered system by a lattice system where you effectively take care of disorder by assigning what is called energetic disorder, and then you have positional disorder. Energetic disorder means that you have sites where, you have distribution of energy states at a particular site, and then positional disorder means that the overlap of the wave function at different sites, they are disordered. So this is within this model, one can show that mobility has this form which contains the information about all those disorders, the energetic disorder and also this positional disorder. And what are the typical behavior which is expected out of this hopping transport? That at very low value of electric field, one can have negative field dependence of the mobility. And then in most of the range of electric field, the mobility, log of mobility is supposed to scale as root over of the electric field strength. And if one looks temperature, dependence of mobility on temperature, the log of mobility is believed to show 1 by T square behavior. So let us try to see how one implements this Gaussian disorder model. So you take the density of states at each site to be distributed according to a Gaussian distribution having certain mean and certain variance. And for the rest of the part, we will not take positional disorder. This is an approximation because, I mean, this energetic disorder will always accompany, will have positional disorder, but for illustration or for simplicity, we ignore that and just look at the effect that what happens because of the energetic disorder, right? And then the jump rates, the probability that a charge carrier jumps from one side to another is given by what is called Miller-Abraham equation, which depends on the which depends on the escape frequency and depends on the distance of sight, distance between I and jth site, and then this is a parameter which corresponds to the wave function overlap. So if you ignore the disorder in the positional disorder, then this is taken to be a constant value for all the sites. And then this is, this depends on kind of, it's a Boltzmann factor. When the site where it's trying to jump has higher side, then it's Boltzmann factor for that. And then the electric field, effect of electric field. So electric field will try to, suppose it is applied in positive z direction, it will try to favor jumps in positive z direction and try to suppress the jumps in the negative direction. And if it is the energy of the neighboring sites where it is trying to jump is less than it is 1, right? So one follows this mechanism, and then the mobility is calculating by dividing the length of the sample over electric field and the time it takes to reach to the end of the sample. Right, so this is more or less the same thing. Right, so in just to say how one goes about doing it is to take a lattice of something like 70 by 70 into 300 array. So it is x, y, and z direction, z being the direction of applied electric field. So one takes a larger length, sometimes the whole length of the sample, and some of the simulations I will show will have the whole length of sample in the z direction and unlimited size in x, y direction with periodic boundary conditions. Okay, so as one does in Monte Carlo, and it is kinetic Monte Carlo, you take typically a cell centered around the site in the question, something like 3 cross 3 cross 3, and look at the all probabilities for jumps, and then you decide where the particle is going to go. Right. So coming back to why negative field dependence at certain values of electric field is expected, it is because at a certain value of the high field regime, your carrier will reach saturation velocity, and then that will not happen. It will also happen for certain low value of electric field, which we'll say see later. And at low values of electric field, roughly, if one wants to understand, the effect of field is to bias the motion in plus z direction, and so that in a way blocks some of the easy paths which would be otherwise available to the charge carrier, and that would lead to negative field dependence at low value of fields. And in intermediate fields, the field is just enough to have its own effect, and then it goes as the behavior log of mu going as root over E. Right. So in this we will consider the effect of morphology. That is, when you have a disordered system, by process of growing or by aging, sometimes it happens that you have microcrystalline regions in otherwise disordered host material, some microcrystallites. So we want to understand what happens when your charge transport occurs through a combination of region which is disordered, and there are certain parts which are not so disordered. Right, so what we do is that we, in this disordered matrix, we introduce the regions of regions with less disorder, right? And then we do the we do the charge transport and see what effects we end up with, right? So, for example, in this we have taken maximum size of ordered region to be 12 by 12 by 100, and which are placed randomly in the disordered host, and the energetic disorder of host lattice, that is the variance of the energy distribution, was 75 MeV, and the host lattice embedded with ordered region will have either 60 MeV, 40 MeV, or 2 MeV. I mean, the less disordered, and we vary that. Right. So one thing is that we immediately see that there is remarkable increase in mobility when you have 60% of regions which are ordered, right? So the question is that why you have only this significant increase in mobility which occurs only at 60%. So in order to analyze that, we have the belief that the mobility should increase with inclusion of ordered region is that by doing so, the charge carrier may find paths which are less resistant. So as we have included the ordered region, we have tried to see what is the fraction, what is the total fraction of the trajectory which belongs to the ordered region. So for 10% inclusion of ordered region, we find hardly there is a fraction which is in ordered region. So it is only that we come around 60% or 80%, then the fraction of the charge carrier's trajectory which falls in ordered region is significantly close to something like 70, 80 or 90%, right? So inclusion of ordered region as such is not guarantee that the charge carrier will follow through that. So this is kind of, I mean, percolation theory would predict that something around 30%, you would have enormous increase in mobility, which doesn't happen here. So, so here, I mean, this same thing that says that the mobility increases only when you have significant fraction of ordered region included in the disordered host. Right, so, what happens to mean energy? I mean, if see, I can have variance, and I can also have a mean of the host region. And so we have considered 3 mean energies for the host, 5.1. Then for embedded region, this host is fixed around 5.1 MeV electron volt. And then we have varied the mean energy of the embedded region, one slightly below the mean of the host and one slightly above the host. And we see that, I mean, this when the mean is also low, that gives rise to better mobility. Now the temperature dependence we see is the log of mobility is depends on shows 1 by t square behavior, and this is significant because in some of the cases where the inclusion of ordered structure was modeled by choosing the density of the energy by 2 Gaussian distributions, that predicted the log of mobility going as 1 by t. So here we see that if we include we include the ordered region by regions, by incorporating regions of varying energetic disorder, then we get back to 1 by t square behavior, which is observed also in the case where you have pure disordered host. So we see that at low value of electric field, applied electric field, we have negative dependence of mobility, and this comes because of, and this becomes very pronounced when you have lower and the sample thickness is very small. So in that case, it so happens that carrier, which is driven by electric field, and also it has to relax in the energy landscape of this disordered site energies, has not come to equilibrium. So that is why for low value of thickness of the sample, the negative dependence of mobility on field is pronounced. So this is what one is showing, that I mean, when you generate charge carriers in the first plane by shining light or applying electric field, it is generated, it quickly relaxes to the bottom density of state, and that would require certain amount of thickness before it relaxes to the bottom of density of state. So if the size of sample is not enough, it will not have that gives chance for this relaxation to happen. So for we have also seen the temperature dependence of this negative field dependence, and we find that when you have large disorder in the system, then this negative field dependence is less. And for a small energetic disorder, this negative field dependence is more pronounced. Right, so we want to know, because I mean this, not only this mobility is a question in this system, some of these results, I mean there is hint that it depends on how carrier diffuses, how it relaxes in the complex energy landscape, also as a function of applied electric field, and also as the function of the morphology which has been provided. We look at the diffusion of the carrier in both homogeneous. By homogeneous sample, I mean that a sample where you have a disordered system, but with one energy, I mean, there is one energetic disorder in the whole sample. And inhomogeneous sample is one where you have incorporated regions of less disorder in the system with varying sizes and varying concentrations. So if you look at this, this is homogeneous sample, and what we are showing is this diffusion coefficient as a function of time in log scale. And what we are varying is the energetic disorder, right? So if the energetic disorder is more, then the diffusion coefficient comes to a minimum, and then it rises. And at even this high times, there is no signature of its getting to equilibrium. And on the other hand, if you see this very small disorder, it decreases initially, and then it comes to equilibrium, this time independent state. And so other things are in between. So now when we look at the inhomogeneous case, where your energetic disorder is this, I mean, you take the disorder of the host with energetic disorder 75 MeV, and then you have ordered region which has 5 times less energetic disorder, and they both have the same mean. And what I am varying is the concentration of the ordered region, right? So for reference, I mean this 0%, so that is pure host, then is the same behavior. And then other extreme is when everything is ordered, so 100%. So that also shows a nice behavior, so it saturates. So it is consistent with the fact that diffusion coefficient for less energetic disorder saturates nicely to its equilibrium value very fast. On the other hand, if you have a mixture, so if you take example of 20%, so you see that it initially decreases, then rises, and then there is a region, intermediate region, where it is more or less constant, and then it starts increasing, and there is no sign of it getting saturated, getting to the equilibrium value. And this happens, and as you increase the concentration, this keeps happening till you reach at a very high concentration of ordered region, where this non-equilibrium behavior is now coming back. So I mean, if you take, for example, 99.8%, so this shows again this behavior. So this effect is maximum somewhere around 86%. So with 86% of the ordered region, this non-equilibrium behavior of diffusion coefficient is more pronounced. So we want to see that what is the origin of this. So in what I showed here, the maximum size of the ordered region was 25 by 25 by 40, so in this we have fixed the concentration of ordered region to be 50%, and we are varying the maximum size of the ordered region, which we could include in the host matrix, consistent with this percentage, right? So so if you see this is original one. So if I reduce the maximum size, then it is this intermediate regime is it's vanishing. So and up to this is 5 by 5 by 5, and then you have mixed distribution where you don't include any ordered region in the system. Just you take you generate you have mixed Gaussian distribution with varying energetic disorder. Right. So this is field. This field is fixed at, for all the calculation now, the field is fixed at 6.4 into 10 raised to the power 5 volt per centimeter. So high field. This is high field. This is very high field. So much more than any one which is shown here. So we are not looking at low field. Right, so here we are seeing the relaxation of carriers. So simple formula: tracking the carriers position, right? So yeah, X. So Z minus Z bar whole square divided by time. This is tracking of carriers, trajectory of carriers. Right, so this is again showing the how energy of the carriers change, right, as a function of time. So when you have the energy, I mean this. If you have this 85% ordered region, right? So for 15% ordered region, it relaxes, right? And then and as you increase this disorder, you see that it has come to more and more this state of lower energy, right? And here we are. So this is all. This is homogeneous sample, right? Here in this you have incorporated the ordered region, and then and these are the percentage of that, and you see how energy relaxation happens, right? So this is this one is 100%, so it relaxes, and then as you increase the, and this is 80% of ordered region, so you see that, I mean, it is taking time to relax to the bottom of energy, I mean density of state. And here what we have done is that we have followed the carriers which are generated in the ordered region and in disordered region, and separately found how they are going to relax. So again, this is we are varying the concentration. So if you see that this is 0% is basically the same disordered host, and then you have this 50 and 50. So this is the field circle is the one which is generated in disordered region, and it relaxes. But if you see the open symbol which represents the charge carriers which are generated in the ordered region, they take more time to relax, right? And this is more or less obvious for all other cases. So it suggests that the charge carriers which are generated in the ordered region, they take a lot of time to relax to the bottom of energy. And here we are doing the same thing. So we are looking the energy distribution at various times. So this is for the pure host. So you have initial density, the density of charge carriers which are generated in the first plane, and then as time goes on, it relaxes to the bottom of density of state because of that Miller-Abraham rule. Now you have 30% of ordered region. So you have this initial density of state, and then you will see this, there is, I mean, you can see here the two distributions, one the narrow one corresponding to the carriers which are generated in the ordered region, and then this also takes, I mean you can see the signatures that it has not, come to, equilibrium, and this effect becomes more pronounced when you increase the region of ordered region. So you can see here also there is a sharp peak which corresponds to the carriers which were generated in the ordered region, and at 90% you can see it very clearly, right? So so this is again showing the density of states as a function of the maximum size of the ordered region, and this is for 25 by 25 by 40, which has been used throughout, and this is by making this size of maximum size of ordered region to be smaller and smaller. So as you see that when, if the maximum size of ordered region decreases, then it nicely relaxes to the bottom density state. So by having a region, ordered region, which is sufficiently large, it inhibits the relaxation of the charge carriers which are generated in the ordered region. Right. So in here we are trying to see the effect of electric field strength. You asked this question. So at various electric field strength, we are trying to see the same behavior. So with increase in electric field, this effect is becoming more pronounced. So so far so good. This charge carriers are basically generated in ordered region and disordered region, and the ones generated in ordered regions take long time to relax, exceedingly long time to relax. So what would be the way of experimentally seeing that effect? So what experimentally one measures is what is called time of flight current pulse. That is, you apply, you apply light or electric field in the first layer of the sample, and then as a function of time you note the current, and typically this shows this kind of behavior. So it has a peak to start with, and at earlier times, this peak is due to the fact that, I mean, when carriers are generated, they relax very fast because of energy differences between the carriers generated and the all available density of states. So this is very fast. Then it becomes drops down, and then this I mean the tail part gives I mean is what gives you information about the slow relaxation of the charge carriers. So this is one defines what is called the tail broadening parameter, and one defines it and measures as a function of energetic disorder, and then one shows that this tail broadening parameter increases with energetic disorder. And this shows that, I mean, this mobility decreases, tail broadening increases, which says that, I mean, this relaxation is taking long time. And so the same, this is simulation of this time of flight pulse, and then this W is calculated, and one sees that when your this W increases to begin with concentration of ordered region, and that is because of this slow relaxation. After a point, something like 86%, this again comes back. So this is the reflection of the same diffusion coefficient behavior, which one can observe experimentally. And again, we have done the same thing, that dependence of this W on the size, maximum size of the ordered region, which we have included in the disordered host. And this also is consistent with what we observe in diffusion, behavior of diffusion coefficient as function of time. So, I mean, to conclude, I mean, we see that morphology and disorder influence the charge transport in a big way. And what needs to be done is to model interface correctly. Here we have just put an ordered region and with sharp interface, which is not experimentally correct. So there would be some smoothing, and which needs to be done. And then we have ignored the effect of positional disorder, so that needs to be included. And then there are proposals that, I mean, it's not necessary that the charge transport in the ordered region also is happening through the hopping transport. So there are proposals of putting some kind of band transport and other models for that, and so that also needs to be done. So with this, I thank you for your attention, and if there are questions, I'll be happy to answer.
So questions?
So you okay, so the first thing is that you don't vary the positional order on your system.
No, we have
disorder, right?
Positional disorder. So I mean, basically, the idea was to first see, I mean, what is the effect of diffusion and relaxation exclusively due to the energetic disorder. Because, I mean, see, people believe, even for negative field dependence, there was belief that it only occurs when there is positional disorder. So the idea was to first see if it comes because of positional energetic disorder by itself. Of course, one has to consider the positional disorder also and see what kind of changes it gets.
Okay, so this is probably a shameless advertisement of what we've done. We've actually done the coarse grained simulation of P3HT, as well as quantum mechanical calculations and kinetic Monte Carlo to look at transport. So it would be nice to actually tally with your models.
Yeah.
Okay. Any more questions? Okay, so if there are no further questions, let's thank speaker again.